Let's recap. The apple accelerates at 9.8 metres per second. The moon accelerates at r omega squared, and it takes the moon 27.3 days to travel 360 degrees round the Earth. So we write omega equals 2 pi over period, and its centripetal acceleration is just 2.7 millimetres per second. So the ratio of the distances is 60, and the inverse ratio of the accelerations is 3,600. Now, because Newton had analysed orbits, he knew that the force that caused them was proportional to 1 on r squared. So here was his remarkable insight. The forces that govern the moon and the planets are not something mystical and remote. They're familiar. They're the same force that gives objects weight on Earth. So that calculation you've done is revolutionary, or at least it was in the 17th century. Before Newton, heavenly objects were thought to obey heavenly laws, completely different from the laws of our familiar, dirty Earth. For Newton, one law applied everywhere. And it was action at a distance, no medium required. Let's look at that law. To get the accelerations proportional to 1 on r squared, the force has to be proportional to the mass being accelerated. The moon in our example. Further, for Newton's third law to hold, there had to be an equal and opposite force on the Earth. So the mutual force must be proportional to both objects involved, nicely symmetrical, as the third law requires. We now call this law Newton's law of universal gravitation, and here's how we write it today. Between bodies 1 and 2, the gravitational force F12 is minus big G times m1 m2 on r squared. The constant of proportionality, big G, is called Newton's constant. The minus sign tells us it is attractive. The force is in the minus r direction. And remember that symmetry. My weight, 700 newtons, is the gravitational force that the Earth exerts on me. But I attract the Earth with an equal and opposite force. My gravitational field is weak, but multiply it by the mass of the Earth, and the Earth's weight in my gravitational field is also 700 newtons, up. Symmetry explains why the force is proportional to both masses. But why is it an inverse square law? Well, there is a wonderful, elegant reason, but I'm going to leave you in suspense until you study electrostatics and Gauss's law. So, how big is big G? The answer is not very. Let's consider a mass m near the surface of the Earth. Its weight is m times little g. And we've now seen that it's also big G times m times the mass of the Earth over the radius of the Earth squared. Set these expressions for the weight equal, cancel m, and we have big G times mass of the Earth equals little g times the radius squared. Newton knew this product, g m Earth, but he didn't know either factor. Of course, he could estimate the mass of the Earth. It must have a density of several tons per cubic metre, and he knew its size. But the only way to know it precisely was to measure big G directly. Well, that was first done by Henry Cavendish. Here's how he did it. 2 large masses on a rod suspended on a weak spring. Only a tiny twisting force is required to turn the rod. I put 2 masses here to twist it one way, then here to twist it the other. Well, you notice that my masses don't seem to be moving. Cavendish used 160 kilogram lead balls and a very weak spring, and still the deflection was only a few millimetres. Newton's constant, big G, turns out to be 6.67 by 10 to the minus 11 Newton meters squared per kilogram per kilogram. Check those units. G times m1 m2 over r squared. Yes, newtons of course. Let's do a quiz to get a feel for the strength of gravity. But one important proviso. In these calculations, I measure the separation between the centres of the objects. This only works exactly if the objects are spherically symmetric and if you're on the outside. Newton worked that out in his shell theorem. It's not in our syllabus, but we'll give a link to it.